So, coming back to my drawing here again, you have seen that something called set is given. When they mean set, it means it is a punch and die system. Okay. So, you have one part of it is the bottom which is here, another part of it is in the top. So, here this is upwards, here this is downwards here. Set drives material and you will end up with any of these operations. You see here bends with a medium wipe, and you see here there is a smooth radius here in this corner. One of these limbs has a smooth radius. So, as we bend it with this operation, it will be slightly different from if it were directly done with a sharp radius. And in this case, you see here, it could be something which is made at a different angle. So, this is a 135 mm angle here, this is 90 degrees, this is 135 mm. So, we have K factor which keeps modifying all the time. In the video which if you have seen the previous lecture, I have shown you a folding machine where we have a finger holding it, and after that the bottom die moves up, the bottom limb moves up, and then we have a neat folding machine. This end, one of the things towards the end I showed you was the V brake. So, we have a punch on top, then we have a die at the bottom, and then you see how the bend takes place here. Here also 3 types are there. One is if you have a gap, we call it air bending. If both sides are pushed and then we hit both of them together, it is called coining. And then we have normal bending which has other operations. In here they have shown a movable rotary bender here. What this rotary bender know? This inside part also moves here and then gives you whatever the natural this thing here. Have you seen here? Instead of that being a rigid thing where it is forced to slide, this part of it moves and bends with it. You see this thing here, this vertical part, no? You see here, then you see how it bends over here. But these are all more details on the shop floor, and depending on for large part production. In the case of small production, it is very unlikely that you will have this. So, you have made things which have a very large gap here, a gradual bend. Neutral axis is exactly 0.5. So, when we go down, they try to come to the, can we have a formula? When a developed length is calculated in radians, the equation is extremely simplified because radian is an arc length. So, no additional translation into angles is needed as a standard formula below. In fact, the standard formula is the radian formula plus a built-in angle conversion from radian measures to base 360. While this is nice for us probably from a physics point of view, the reality is that we need to mark them in decimal millimeters. So, we have a height gauge where the height gauge somebody has to put the sheet that needs to be formed against a vertical surface and then do that. In that case, talking about things in radians for angles in radians, it does not make sense, but here it is about A is the angle in radians and then how to come back to making things understandable. So, in this part of it, I will cover in one of the other lectures. So, what is done normally is, depending on the practice in the workshop, you usually have a table. In the case of the place what I have shown you, for all our 1.6 and 1.5 mm aluminum materials, an allowance of 0.65 millimeters is added to the internal dimensions. So, you have a simple L, I have limb A, I have limb B. Suppose this is 40 mm and this is 40 mm, I take the two internal dimensions straight away. Mind you, I am not talking about the clamping position, I am just talking about the flat length. When it is laid out, how much flat it will come. So, this is what I tried to show you that day. So, I have a flat piece, I have internal plus a little bit of bending element. So, in our case, there are 0.5 mm radius and all that, we come with 0.65 millimeters. So, we try to include that in various development calculations. But if you come here, very elaborate thing saying for all other angles where A is in radians, elaborate calculations are given here. We have single hit Z bend, or when a Z bend is hit in one hit, the middle panel will stretch more than expected. This is because the middle panel is trapped between two V forms. Typical example might be a 0.32 bend with 0.06 material, which might elongate by 0.01. These are inches. I think correspondingly you may have to calculate the length that is there. This in relation to the bending machine we have in which I have shown you in the video. In the bending machine which we have fingers, that part which is under the fingers, that part, the clamp part under the fingers does not change in length. And then to accommodate for the internal radius, we also mark 0.5 mm inside. So, if you want the internal dimension, let us say internal dimension you want around 12 millimeters, we mark 11.5 millimeters here and clamp it like this. Advantage is now eventually internal dimension of 12 millimeters you get, thickness is extra. Now, if you come back to the see here, this is the developed portion of the that same box which I showed you here. However, still to avoid confusion, you see here we have a little confusion here actually. This width cannot be this much, it needs to be a little smaller or it needs to be bigger. In case it is overlapping this, it needs to be two thicknesses wide compared to this. In case it is coming inside, you need to have probably two thicknesses smaller. Otherwise, we end up with a corner which is not filled, the corner will not be filled. So, I can see edges of both the sheets in the corner. This is in one shot, if you are trying to make any of these angle. Where do we have these things? Wherever you see where a thin sheet is there and it requires a little bit of strength, as you would see a purlan, or I do not know how to pronounce it, to make sheet stiff. Inside the spot weld items like this here, and if you see the proportions of it, typically the total step what we get is about 4 to 5 times the thickness of the material. So, without occupying too much space, we can make sheet stiffer by putting these Z purlins inside the sheet. Fabricate it, once again we end up with these things, and then generally it is very rare to see any part making a single function, that will be an over design. So, instead this may be also used as a catch or as one of the closures of the cover, or a panel which slides, or something to compensate for a thickness. So, you see here, imagine something like this is there, something like this is here. Imagine one more sheet can come here. So, this can form, if one more L comes here, this can form one edge of the thing. This could be the bottom part, this could be the top portion, and between these two the thickness can probably be covered by a gasket which ensures that there won't be any leakage between the two panels. So, if this were to be the top, there can be a bottom here. For example, a chassis can come here, this could be the top cover, and in the bottom chassis, if I pack the inside surface with a suitable elastomer which is probably stuck on one side, then I add a gasket grease and then push it on top of it, I can avoid and make it splash proof. So, if normally water to enter here, it will not try to go inside. So, you see here, for if we can combine the features of something that does this, and that is, it adds a little bit of strength, stiffness, plus it helps in the overlap of the materials, it takes us on the way to our product design. So, if you have completely closed, wrapped hem development should be treated with caution. While they will generally develop with some 0.3 K factor, they are at a minimum made with a 2-hit process and subject to a bit more variation. The part has reasonable tolerance, then the risk is minimized. Wrapped hem is used as a safety edge or a cosmetic feature. So, this is where I would like to say, instead of just saying it is a cosmetic feature, it is something which will ensure that you do not have sharp edges, plus it also adds that little element of interest, and as it goes in design, if you cannot hide something, they try to highlight it. So, we get things like this. A wrapped hem will see a significant backside thinning, which is usually influences the leg length. If you see fully, if something is closed like this, if something is fully closed like this, so even the details about how much of this extra length is required for a given a development length. It is not just about one more time now taking the inside lengths and then calculating a average of the spherical, I am sorry, of the circular length, and then expect the total thing to come normal. When you fold something like this, automatically you cannot expect all this to behave perfectly like this. You have a circular portion which is also deformed. So, in this case we need to take care of all these things. Is it important, and why is it that I am talking about it? Yes, it is important, because whenever these features are added, you may not have any space inside your basic equipment, and it should not interfere with something. So, next time you get a chance and you open a cover and see that whenever such things are done, usually additional reliefs are also given, so that some cable may have to enter, or a cable grommet needs to be placed. While a cable grommet is designed for one thickness, and this place where that folded over 180-degree bending is there, there will be an additional thickness which may need to leaking. So, a probably 1/4 or 1/5 arc of a material is removed there, remaining bent over, and then the grommet can sit comfortably in that, and the grommet can be, if we have two closures like this, in between thing. So, you have a little offset here, I can't do it and then in this portion you probably need a cut here and one more cut here to make sure that a grommet can be inserted here. In the power supply which I showed you first time, it was there. So, materials are often tried and specified also, saying can you make a 180-degree bend. At this point it will become obvious to you that if the grain structure of it, that is, if this is the rolling direction of it, it obviously bends easily. But if the rolling direction was this of the raw material, chances are it will break here. So, we are in trouble. Now, imagine you want it a little stronger, probably we would like to have one more limb this side. So, is it alright, can we make it with this? That point is where the designer will take a decision. Probably they will put an L-shaped length here inside separately, have this and join them together, or have a dimple or something which once it is formed it stays stiff, which will take me to the last but one what do you call page, saying in case you have a simple thing there was a large difference in the offset. You understood, no? Almost like this, it was something was here like this and something was here. Here typically this is much less, seen that, no? Suppose there is only one thickness offset. In this case the neutral axis is likely to not have too much of a additional effect. So, here length is only slightly longer. When they talk about slightly longer, it is probably not even measurable. It should be the order of 0.05 or 0.1 millimeter long, and then it does not matter because the limbs themselves, no, the order of limbs are so small. So, as you go down, when a part has a gusset in a formed flange, the gusset area will form high. What exactly is a gusset? So, whenever we have a L angle like this, so stiffen this angle in one of the corners, suppose this is a thing, they make a depression which goes inside. This is the one makes the part stiff. So, next time you open any hardware around your house, typically opening fans, or if you are a hobbyist who likes to check things in a washer, a dishwasher or a washing machine, you will notice that though the material itself is probably a good 1.6 or 2 mm steel, though it is at a right angle, they usually make a dimple on one side so that it comes in, and then over a length like this, let us say over length of about 100 millimeters, every 20 or 30 millimeters you have those dimple. If you have 3 of them, say 25 mm apart, it will make it very, very strong. Now, slowly what was a simple bend, an L bend, is getting complicated because that gusset part of it, that small dimple what you give in the corner, will now add to all these calculations, and this is not done in an ordinary machine. Probably the die part of it has a relief, but the punch part of it has been built separately. So, if you see that V bend what I was talking to you about, when we have that V forming, so a lot of detail is added here to see that the required bends and all take place. So, as we come to the end of it, this is where I thought I suggest you read this, go to the, it is old, it is probably practically 15 years old. All suggestions are for training, author is not liable, though I am not the author, I am just somebody who is reading out for you. Usage of this information and misapplication is your risk. You may use, reproduce and print as long as it remain in the original format. Hence, I have helped you along by reading along what has been done here. So, separate release is not required. Now, I will try to go to the, this is taken from again a what you call an agency which carries out these operations. I just need to allow you to probably read what is written here. Okay, I will just, the difference there is all about the K factor, saying how do you determine the K factor, and the word something called scientific and the word trial and error are used. Instead here this is more related to if you take the internal dimensions minus the bending radius, how do you add a bending allowance, or in the case you want to take the external dimensions, add the external dimensions and then you remove the internal dimensions. So, we once again I will able to Read this first part of it, just read it. It's a manufacturing process. Metal can be deformed by plastically deforming the material and changing its shape. Material is stressed beyond its yield strength, but below its ultimate tensile strength. That is where it continues a little ductile. Ultimate tensile strength will make it fail, it will break, which will happen in the case of 180-degree bends. Sometimes if you do not allow it to form itself at a given rate, if you do it, it is also a rate phenomena. Yield strength is where the bending takes place, and then if you remember our curve, stress strain curve, you will see there is a small kink, and then there is a residual permanent strain which occurs. We use that residual permanent strain before it fails completely, and then the yield strength. There is little change to the surface area. Bending refers to deformation about one axis only. Here again it is very important, we are talking about only one axis. So, if you take our plane as the xy plane, the one away from front to back is the one. Alternatively, if you are in the horizontal surface, x is in the horizontal, the y direction only. So, if you have an axis between the origin and the y axis, and if you bend things over, this is what about one axis. Bending is a process by which variety of different shapes can be produced. The use of standard die sets or bending breaks. So, if you read my, or if you read these notes, very important things are there. See this, one of them it says is, I will try to highlight it by going a little closer. Standard die sets or bending breaks. So, bending break is what I showed you already. Then what is a standard die set? Things like joggling and several other operations including lugging, and those things use standard die sets. Meaning the design is a standard, it is not as if the whole thing is not just whole thing is not a standard. Material is placed on the die, positioned in place with stops and or gauges. Very important, very important thing, saying everywhere we have a backstop. If you want 10 millimeters, it is not every time we do the marking, it is not real. In the case of mass production, it is not worthwhile marking every sheet. So, instead one sheet is marked, and at the back a stopper is put. That stopper, it will ensure that next time you need not mark it again. So, maybe 100 pieces can be done, you just feed it into the area of operation and keep doing. Or other is about gauges. Instead of a stopper which is fixed, it is possible for you to have a gauge in the front where you can read what you need. You can have the gauge in the front or the back, you have a scale, and then you unlock that stopper and move it to a necessary thing, and then your operation is done. Coming back here, it is held in place with hold downs. Upper part of the press, the ram with the appropriately shaped punch descends and forms the V-shaped bend. It is nothing but what I have already shown you. Again coming back, maybe when I get a chance, after we finish this little bit of reading, we will go back to the workshop and see if we can make things little more clearer. Bending is done using press brakes. Press brakes normally have a capacity of 20 to 200 tons to stock from 1 meter to 4.5 meters. Larger and smaller presses used for diverse specialized applications. Programmable back gauges, multiple die sets currently can make bending a very economical process. I think I will stop here for today, and we will continue in the next lecture. I will once again start with this. After we finish 3 of these things to read, So, if you remember, I have just lowered you into this small thing about a bend allowance and a bend deduction. Contemplate on this. Alternatively, if you can locate another resource, read it. So, thank you. I will stop here.